So, third in our series of magnetism. So we have seen how the magnetic force and field both looks like and differs from the gravitation and electric field. We've seen how the force works a little bit different with polarity and poles rather than positive, negative charge or with mass. We have seen that you have to have two ends of a magnet, north and south, unlike charge, which has I could have positive, I can have negative, I can have positive and negative. Um, and then we saw that we can map the magnetic field using the compass, our detection device for the magnetic field. But it doesn't explain why that hunk of iron has a magnetic field. Okay, so what our goal here today is to figure out what is the source of magnetism and move from there. So let me share my screen so we can look at a demonstration and go from there. Okay, so there you go. You can see that I have a wire taped down to the table here. And then near the wire, I have a compass, our magnetic detection device. And right now, you can see I have a battery, but no closed circuit, right? That's there. So this discovery was accidentally made in the 1820s, specifically 1820, by a scientist whose name is Hans Christian Ørsted. I'll spell that later. It's a fun little O with two dots over it, the umlaut, that makes it have that sound. And it was discovered totally by accident. So what was discovered was if I have this wire, and notice it's sitting here, and it's pointing due north right now because it's sitting in the Earth's magnetic field, that if I close the loop and thus current starts flowing, I want you to see what happens. See that compass, as long as I have the loop closed, points perpendicularly to the wire, right? That must mean when there's a current flowing, that wire produces its own magnetic field. And specifically, that field was pointing there. Now, I'm actually going to put the compass underneath the wire. And notice it's pointing here. Now, remember what we saw before, and it only flows while the current is going. That means that the field must be going this way above the wire, and then this way, oh, sorry, you can't see that, this way below the wire. And we said that all magnetic fields form closed loops. So in this case, the magnetic field is going to be curling around the wire. Okay. Now, something even more. So let me put that wire there. You'll note that the magnetic field is now going in this direction towards the top of your screen. And now what I'm going to do here is I'm going to flip the terminals or where the wires are going. So now the current is going to be going in the opposite direction with that wire. And notice now the magnetic field is going down towards the bottom of your screen. So meaning that what's causing this magnetic field is the current through the wire, and the direction of that current affected the direction of the magnetic field around that wire. And it is indeed around that wire in a loop. And I could literally put the compass at every point around that and see that loop around. In fact, I'm going to do that, but with a slightly different system. Okay, so I'm going to just get this settled. Okay, so what I have here is a wire, and actually you can see it in cross section. There's a loop of wire here. And so what I have here is you can imagine that this wire is going down into the ground there. Okay. So let me just set this up. Boom, boom, boom. There we go. So when I close the circuit here, there's going to be a current going through this wire, through the loop. So down to the earth, towards the bottom of the page, up to the sky, towards the top of the page, and then right there. So what we're interested in is this space right here. Okay. So what I want you to notice here is when I move the compass around here, its direction is not changing, meaning it is not experiencing a magnetic field due to that wire at least. So now I close the circuit. Sorry, it's a little messy over here. Boom. And all of a sudden you can see that there is a magnetic field looping around that wire segment, pointing to this side here, right? here, here, here. And what you'll notice is at every location that magnetic field, so if this is the magnetic field, or this is the current, that magnetic field was pointing like this at every point, meaning it was acting perpendicularly to the current, sort of like on the tangents of a loop. So we're going to draw that now. So before we get too far, let's just do some quick vocabulary. The thing about magnetic fields, which makes them difficult to think about, is all magnetic field pictures are 3D spatial, right? Because what we had there was a wire that was going like this and a field that was going like this. So 3 dimensions are involved. So the directions that we're going to talk about are to the top of the page, to the bottom of the page, to the right of the page, to the left of the page. We don't want to say up, because if I ask you to point up, two things might come to mind. If you're looking at me here in the screen, I might point towards the sky, but reasonably you might think up on the picture here is this way, and those are two different directions from one another. So the words up and down are really problematic when you're talking about magnetism, unless you are talking about in the world, and I'm talking about up towards the sky and down towards the ground. So here we go, top, bottom, left, and right. We also need something for into and out of the page. So this is an earlier notation. X with an X means into, and a dot means out of. And the argument we made before about that is, imagine if I shot an arrow at your eye, you would be looking at the dot of the center of that arrow coming at your eye. And if I fire an arrow away from me, you're looking at the fletchings, the feathers on the back. So what we had there was a wire. And I want you to imagine I have a wire here. You actually don't have to imagine I have a wire. I literally have a wire. Okay. And that wire I'm holding like this, up and down. And I can imagine if that wire kind of like pierced through the page. So that is what we're talking about. So if I put a current through that wire is either going to go into the page or out of the page. So what I'm going to draw here is just a cross section of that wire. And I put an X in it because I'm going to pretend my current is into the page. So there's your current acting into the page. So what is the rule? The rule is something that's called Oersted's law. And Oersted's law says currents cause magnetic fields. Now, we have a more modern notion of Oersted's law because we now know what a current is. A current is a flow of charge. So that means moving charges cause magnetic fields. Now, when I say a current in our class, I mean a flow of electrons, and that's going to become important in a minute. And what's true about that magnetic field? It always forms a closed loop around the current. Okay? So in this case, that must mean that our magnetic flux line or magnetic field lines look like that, closed loops around it. But if I were to put a compass in this location, right, that compass would point in a very specific direction. How does the compass point? We would say that the field created is always perpendicular to the current that creates it. Okay? So in other words, if here, that field must be, since that is the direction of the current flow, that perpendicularity is either going to be this way, this way, this way, this way, but because it's a loop, it's constrained to be either this way or this way. So which is it? Well, essentially what we did is lots of testing. Over and over and over and over, get tested, and we figured out a pattern. And then once we figured out the pattern, we figured out a mnemonic device for that pattern. So I'm going to actually stop my share for a second because I think it's going to be easier if you're looking directly at me as I do this. Okay. And this is the mnemonic device. So what I did is I took my left hand, and the reason why it's the left hand is because we agree that a current is a flow of electrons. If we lived in magical engineering land where they believe in the magic of moving positive charges or moving holes as we describe them, I would be talking about right-hand rules. Most commercial textbooks talk about conventional current and right-hand rules, but folks, what's moving? Electrons are moving. So why wouldn't we describe it in terms of what's actually happening just because there's a convention? That's my beef with engineers. But anyway, we are learning left-hand rules. And the gesture we're going to make is okay. So notice here, I've curled my fingers and I have my thumb perpendicular to the plane of my curled fingers. So everything is okay. And if you just think everything's okay, you're going to be fine with our hand rules. And so what is this going to look like? Now, remember, this is a mnemonic device. We took actual compasses and put them around to figure out what actually happens. But here's what the rule says. The rule says do the following. Here's my thumb. Here's it. Okay again. I'm going to point my thumb in the direction of the current flow. In that case, that's into the page. My fingers curl in the direction of the field. So notice that would mean curling around like this, or in this case, counterclockwise. Okay? Counterclockwise. And that is what's known as the first left-hand rule. So the first left-hand rule, it is designed to find the direction of magnetic field around a long, straight wire. How do I do it? Thumb in direction of the current, fingers curl as the field does. Okay, we're going to do a whole bunch of examples now. So now imagine here's my current, but now my current is out of the page. So here's, I'm okay. So I point my thumb in the direction of the current, and you can see my fingers curl around like this. Curl around like this. And that's what the magnetic field surrounding that long straight wire looks like. Let's do another example. Let's say that my current goes to the right of the page. So I don't know, this is a section of a circuit. So now I'm going to point my thumb in the direction of the current flow, but this is really weird because it's really hard to curl, right? Because I got the table in the way. But if I had to curl, my fingers would go into the page here. And then they would magically come bursting out of the page down here. And so that's what the field looks like around a wire segment that looks like that. And you can imagine the field looping around like that. So over the top of the wire, so if I'm magically floating my compass over the top of the wire, the field would be coming out of the page here to the top of the page, into the page. And if I was able to tuck the compass below, it'd be pointing to the bottom of the page. Okay. And so that is the first left-hand rule. Now, we're going to look at another system. I don't know why my brain just stopped there. And I'm going to look at a loop of wire because oftentimes we have loops of wires that have currents going through them. We call them circuits. I'm going to draw a circuit. Okay. So as we know, negative, positive, delta V, R, delta T, and this would have a current flowing through like this. So here the current is going clockwise around the circuit. So I can use my first left-hand rule to figure out what's true about the magnetic field around each segment of wire. So here, that's literally the problem we just did. I would end up with using the first left-hand rule. Pardon me a second. Point my thumb in direction of the current. My fingers would go into the page here and go down to the bottom of the page, and then out of the page here. Great. Now this segment of wire. So now my thumb is pointing to the bottom of the page. Notice I would go in over here and then scoop around. Oh, it's so hard to show. And come out over here on this side. Here, I would point my thumb there. It's actually easier to show. It would come out there and then go in. So if I go in over here, it's so much easier in person, folks. And likewise here, if I did that here and here, I would get the following. What you'll notice is when the current goes clockwise around it, the field inside that loop is entirely out of the page. And outside the loop, it's into the page. Right? So there we go. what we're going to do now is we're going to create something called the second left-hand rule. And the second left-hand rule is used for a loop or coil to find the magnetic field at the center or inside of the loop or coil. Now, what do I mean coil? I'm talking about something like this, a coil of wire, right? You can see a coil of wire there. Let me go actually grab a better coil of wire. Here's another coil of wire that I have, right? You can see that there. Oops, see that there. And a coil is just like a stack of loops. That's all it comes down to. And we'll talk about coils in just a second after we establish the second left-hand rule. So what does the second left-hand rule say? So it's to find the direction of magnetic field in the center. Now I can see inside the loop that the magnetic field is out of the page. So here's what we're going to do. We're still going to use our same gesture. Everything's okay. Everything's okay. In this case, though, we're going to curl our fingers around like the current does. So this current goes clockwise around that loop. Notice my thumb is pointing out of the page, which is exactly what this field does. Huzzah, there it is. So the second left-hand rule is curl your fingers in the direction of the current, and your thumb points in the direction of the field inside the loop. You can't see that. Your thumb points in the direction of the field inside the loop. So there you go. So we're going to do some demos with a coil because it's really neat. So I've got this coil here, and I'm going to attach my battery. So to run a current through that coil. Get this going. And let me just show you right now, in this region, the compass is not reacting. So there's no magnetic field. So now I close the circuit, and you'll notice there was an immediate reaction there. There is now a field pointing in that direction there. And notice that that field loops around the coil. Loops around the coil. That should remind you of something. That field should look suspiciously like the field that we saw around the bar magnet, because it's the same shape field. I'm going to put that there. I'm going to sprinkle some iron filings and show you that we're going to get the same shape field. Can you see that field looping around there? And now you can see the closed loop itself because we can actually see down the center of the coil. I can't leave that on long or the wires start to burn. You'll notice they're already a little toasty, right? So that's what I mean by the closed loop of the magnetic field. How cool is that? All right. So it gets even better. What we have here is a magnetic field that I can turn on and off. And not only a magnetic field that's shaped identically to a bar magnet that I can turn on and off. This is the basic idea of something we call electromagnetism. Okay. And this is our ability to create, electromagnetism is a bunch of things, but one of the main things is our ability to create what we're called electromagnets, which are temporary magnetic fields using coils of wire. A coil of wire comes up so often in physics, it's given its own name. It's called a solenoid. Well, I don't think I said that in class, but there it is, right? To get an electromagnet, that temporary magnet, I'm actually going to grab something else. Here we go. Notice here, I have a coil of wire. I have my, I have my compass. So I'm now going to connect this to the battery. Oh. Notice the coil is doing nothing. I connect it. Now I have a current flowing, and I've got now There we go. So this must be acting, whoop, there we go. It's not a very strong effect, right? Well, I can actually change that effect by doing something. Watch this. I put an iron nail down the center of my coil. Let me just, that's fine. Turn it on. That is a much, much stronger reaction, okay? And I can manipulate the strength and direction of that magnetic field by manipulating some stuff. So here we go. What's an electromagnet? To have an electromagnet, I need a coil, which is just a stack of loops. I need a current. And what I need is a core. A core, that's just the material at the center of the coil. Now, you'll remember initially I had nothing in the core, right? It was just a loop and there was air in the center. And then I put the iron nail in it and the magnet became much stronger. So the strength of the field created there's a couple of factors that affect it. One, is the core permeable? Okay. If I use a permeable material for the core like iron, nickel, or cobalt, it drastically jacks up the strength of the magnetic field. So if yes, it is a strong field, and if no, it is a weak field. So I still got a field with air as the core, but not much. The next thing is the number of loops, as well as how tightly packed they are. More loops, more field. Why? Folks, every loop creates its own magnetic field. So if I stack loops, I'm stacking fields. The law of superposition tells me I'm going to get a greater field if they're all stacking fields that point in the same direction. More current, more field. Okay? So I get the strongest electromagnet with a high current going through a coil with lots of loops and an iron core in the middle. This electromagnet is exactly what's inside of an MRI machine. They use intensely strong magnetic fields. I told you the Tesla was the unit of the magnetic field. These crappy magnets that I've been using, they're like 1/100th of a Tesla. The Earth's magnetic field is like 1/10,000th of a Tesla. In a MRI machine, they're like 5 or 6 Tesla. A Tesla is a massive magnetic field. I don't know if you've ever seen the things at the junkyard that pick up the cars, not the claw. I probably should not do it. It looks like a little metal disc. That's an electromagnet. And it puts it on top of the car and lifts the car up. Those things can produce magnetic fields of like 20 Tesla. They're amazing. Okay. So what we now need to do is learn something about that electromagnet. So I'm going to draw one. So here's the core. So that's going to be the thing I'm going to wrap my wire around. So I'm going to show a wrapping of a wire. And this is a very clever picture that uses some good perspective. So what I hope you notice here is that I'm drawing a wire that is going, so if this was the core, I'm like taking my wire, I actually do it, and I'm wrapping it like this around. So between my face and the core, that's where the wire is, and it goes behind, then in front of, behind and in front of. So here we go. If I have a current that runs like this, I can see that in front of the core, the current is running to the top of the page. Then it goes to the bottom of the page, behind the core, to the top of the page, to the top of the page, to the top of the page, top of the page, behind the page, okay? And so what I'm going to do here is I'm going to use our second left-hand rule. Remember, it's okay. It's okay. So if this is the core, what my current is doing is it's going to the top of the page in front of the core, and then to the bottom of the page behind the core, and my thumb is left pointing in the direction of the magnetic field through the coil, right? So there it is. And we said that this forms a field, this forms a field that looks like the bar magnet's field, so it's going to loop around like this. Okay. So notice here, the field is coming out of this side and the field is going into this side. So what did we learn about fields when we did them before? We showed that if I had a compass, if the compass points in this direction, that must mean because the north pole of the compass is pointing in that direction, it's being repelled from another north. That must be the north pole of this compass. That's the south pole of this compass. So I can use the second left-hand rule. Whatever direction my thumb is pointing inside the coil is going to point towards the north pole. Let's do another example of that. I'm just going to do a different orientation so we don't get too hung up. But we're always going to have wires that go in front of the coil, front of the core and behind the core. So there we go. So here my current goes to the top of the page, to the right of the page. It's going to the right of the page in front of the core, to the left of the page behind the core, to the right of the page, to the right of the page, and there we go. Now, once again, if I have my core, I'm going to wrap my fingers in the same way the current is wrapping around the core. I notice my thumb points towards the bottom of the page, making this the north pole, that's the south pole, and this is what the field surrounding that would look like. And there, folks, are electromagnets everywhere. A magnet that I can turn on and off at will. Give you an example. In your car, when you press the little button to open up your car, what ends up happening? It's an electromagnet. It pushes something out of a lock. And then when you click it again, it pulls it back into the lock. So it creates a little temporary magnetic field that creates pushes and pulls on other magnets, right? In fact, most buttons that you are pressing in your world are turning electromagnets on and off. Let me give you another one. In the school, have you ever noticed that whenever there's a fire drill, all the doors close simultaneously? Isn't that weird? Well, next time you're in the high school, go look near the door. You might have seen these chains with a little metal disc pressed up against another metal disc on the wall or on the floor. The discs on the floor and the wall, if you look at them, they're not discs. They're coils of wire wrapped around an iron core. And there's a constant current running through those, making them a magnet that the door plate is sticking to. And then when what ends up happening is when there's a fire alarm, all of the doors, the current shuts off automatically all together at once. And so therefore there's no magnet and the doors close. Oh, all of the door little things are in a series circuit. So turning off one of them turns off all of them. Isn't that neat? All right. Anyway, so you have to be able to, with an electromagnet, look at it, be able to identify where the North Pole is. The other thing is, if I were to ask you which of these two electromagnets is stronger, there's a couple of questions you could ask. Are both cores ferromagnetic? If the answer is no, the one with the iron core is always going to be the stronger field. Always, 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 always. Let's say that both these have iron cores. Then you say, oh, maybe one of these currents is larger than the other. Okay, so the one with the larger current would be the one with the larger magnetic field. But let's say I told you that the currents were equal. Which has the largest field? And the answer is this, because there's more coils. Coils, core, current, strength of a magnetic field due to an electromagnet. So that's the last thing we have. That's the last thing that you need to know for the final exam. Now, I'm going to just do one very quick thing because I just don't want to leave it resolved. My hunk of iron that became a permanent magnet, right? What's going on there? Well, clearly there's no current flowing, right? There's no battery, there's no wires. It's just a hunk of iron that's displaying this effect. Well, if we zoom in real far, we can start seeing some currents. Because if we zoom in far enough, we get down to the atomic level. At the atomic level, I have the iron atom and electrons orbiting. Now, this is, by the way, there's more advanced notions to this. I'm giving you the very simplified version. It's enough of an argument for right now. If you go on to college, you learn more truth than what this is. You can peel back the layers of the onion later. We're going to go with these. But imagine that each of those electrons in its orbital produces its own tiny little magnetic field. And you're like, okay, well, why does that mean that the bar of iron, the macroscopic thing, has a field? Well, there's something very special about iron, nickel, and cobalt that allows them to have fields. So I'm going to maybe damage your brain again for a second. We're going to go back to the periodic table. Up. No, show me my periodic table. Ugh, sorry about that, folks. Ugh, not very clear, but we said that iron, nickel, and cobalt right here, smack in the middle of the transition elements. And I wonder what you remember about the transition elements, specifically about the period 4 transition elements. I hope you remember from chemistry, S, P, D, F orbitals. Maybe you do, maybe you don't. Uh, Anyhow, what you might remember is that electrons fill in orbitals in order to achieve lower energy states. And that there were ways of filling those orbitals. And you remember these diagrams that you had. And hopefully what you remember is when you start getting to the transition metals, you had more electrons because we are talking about higher number of electrons, like iron. Iron's 26, so it has 26 electrons, right? So if you remember this, the way that you filled in these diagrams was by doing these up and down arrows. And you filled up your s orbital before you did anything else. And you filled up your p orbital like this. And then you put the down arrows, right? Right. And that was 1 electron, 2 electrons, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then you went back 14, 15, 16, 17, 18. And then we went to the f orbital, right? Okay. And what I hoped you remember or knew is like, what are these arrows about? Folks, those arrows were talking about the direction of the little magnetic field formed by the orbital electron. A filled s orbital has an electron that creates a magnetic field that's oriented in one direction, and its partner is another, so that those magnetic fields cancel out because you create a more stable atom when it doesn't have a net magnetic field. And so what ends up happening is these orbitals fill up such that you have all these, what remember were called spin up. But when you completed the orbital, it doesn't now have a net magnetic field. The transition metals, folks, have a lot of unpaired electrons, meaning those atoms have a lot of small little magnetic fields that are all pointing in the same direction, which yield larger net magnetic fields. So that's what's so special about iron, nickel, and cobalt is that they have stable structures that create net magnetic fields, excuse me, per atom. And then iron is structurally such that I have this atom's iron atom's field might be like this, but this one might be like this. In iron, a lot of the adjacent atoms will have aligned magnetic fields. And the way you turn iron, a block of iron into a magnet is you take the atomic fields and you align them all together to create a larger net magnetic field. And that's actually the process of magnetization, is aligning all of these fields. And the way you do it is you just put it in a large, strong magnetic field, and the internal atomic fields align. It's a little bit more complicated, and that's a lot more complicated than that, but that's the general gist. And it's only structures like iron and cobalt and nickel that have stable structures of nuclei that, or sorry, atoms that have net magnetic fields that are able to align and then remain aligned that create our magnet. So you might say there's no current there, but on the atomic scale there is. So hopefully through this video you understand currents cause magnetic fields. The magnetic fields caused by currents are in a very particular shape of a loop, and our hand rules tell us what the direction of the field at any point along those loop are, and that we can make strong magnetic fields by having coils of wire, which are made of loops of wire, and create a strong magnetic field by having a large current, a ferromagnetic core with lots of loops. And we can predict what the north pole of a magnet of an electromagnetic is. And with that, that is everything you need to know. So good luck.